Okay, so where were we? Yeah, so taking the derivative. So would you guys talk to me about how we're going to take this derivative? So what do we do? I've got, talk to me about like, what? Okay, that'd be a good idea. Why don't we make that a 1/2 power? In fact, let's write it that way. So y equals x times the quantity 4 minus x squared to the 1/2. I like it. So go. What do I do? Yeah.
Would it not be easier to leave it like that when you do the product rule in the square root and then just write it like that when you differentiate?
Leave it as a square root, you mean?
Yeah.
I mean, you can. That's fine. You don't have to write it with a 1/2. You know it's a 1/2 power. Are you saying like, I think I know what you're saying. We'll look at it both ways. That was my plan anyway. Okay, so what do we do when we differentiate that? Okay, so what do we call that? Product rule, right? So we need product rule. So y prime equals, let's do it this way. So we can have the positive term first. Let's do the derivative of x first. So we get 4, we get the second factor, 4 minus x squared to the 1/2 times 1 plus x times what? Right, I got to do the derivative of the second factor. So I need a 1/2, good. So I'll just put that 2 on the bottom, 1/2 to the negative 1/2 times. Okay, good. So we could do a little bit of canceling here. Fortunately, those 2's cancel. That's kind of nice, right? And then if we clean that up, we get y prime equals 4 minus x squared to the 1/2 minus x times x is x squared. 4 minus x squared to the minus 1/2. So now there's a couple different ways you can go with this. Jake, you had an idea. What were you going to do?
Well, so what I was going to do was I'd rewrite 4 minus x squared to the 1/2 of the square root.
Okay, so one way to do this. One way to do this would just be to make those into square roots. That's fine. Square root of 4 minus x squared minus x squared over, I get a negative 1/2, so over the square root of 4 minus x squared. And then what would you do from there? What do you mean? Okay, think about that. So if you do it this way, what you're really doing is you're converting these into fractions, right? And if you're converting them into fractions and you're going to add or subtract fractions, what do you need? Common denominator. So what would I do to get a common denominator? I got to do something to that first term, don't I? Okay, so I'm going to multiply this guy by square root over square root, right? Okay, so then that's just going to give me 4 minus x squared over my common denominator, 4 minus x squared, right? Everybody see that? Because what did we do here? We multiplied we multiplied that by the square root of 4 minus x squared over the square root of 4 minus x squared, right? Okay. And we get all this, and then I can combine like terms. And that's 4 minus 2x squared over the square root of 4 minus x squared, which is 2 times 2 minus x squared over the square root of 4 minus x squared. That's fine, right? That's one way to do it. So the way we talked about it, you take your pick. I kind of like to do it a different way. I kind of like to do it where you just factor out like powers. So do we see any like bases there? Powers with like bases. This guy, right, yeah. So this one, those are like bases, so I factor out the least common power, right? So I can only take out the smallest power with that base, which is this one. So I'm going to factor out a 4 minus x squared to the minus 1/2, leaving behind what? 4 minus x squared, right? Because this is going to give me what's left behind. If I factor out a 4 minus x squared to the negative 1/2, I'm left with that base to the 1/2 minus negative 1/2, right? Which is 1. And that shouldn't be surprising, right? We know it works that way because these differ by 1. So one of them is going to go away and one of them is going to have an exponent of 1. And then over here, that one goes away completely. So we get that, right? Okay. And then in a few short steps, that goes to the bottom. If we combine like terms and factor out a 2, that just gets us right where we got on the other page. Right? So what are our critical numbers then? Where the bottom, so the function, the derivative is undefined where the denominator is 0. So where would that be in our domain? 2 and negative 2. But those are the endpoints of my domain, right? So we're gonna check those anyway. I mean, you call them critical numbers. You could, but it doesn't really do us any good. I mean, we'll put it in our table. We're looking for mainly for interior critical numbers. Where would those be? Say it again? When the numerator equals 0. And when does the numerator equal 0? That's going to be when x squared equals 2. So x equals what? Plus or minus square root of 2. Good. So we get some critical numbers. So if we go to the next page, we can start to fill in some stuff. We know our domain went from negative 2 to 2. We had zeros, we had undefined first derivatives there. And then we had, let's see, we had negative square root of 2, positive square root of 2 were zeros of the first derivative. So what's going on there? Horizontal tangent. Okay. Now, if we're trying to figure out everything, and let's say we are, inflection points too, what do we need to do next? Second derivative, yeah. And where would we go for our second derivative? We probably would, I mean, we can do this as either a quotient or a product. Take your pick. I guess it's a quotient, so let's just do it as a quotient. We could, like, you mean like right there? Yeah, you could do that too. But if you do that, you're still going to have either a quotient or a product here. So we might as well do it where we only have one instead of two terms. Okay, so if we use our quotient rule, okay, what do we get? Quotient rule. So, yeah, so low, and I'm going to make that a fractional exponents, right? So 4 minus x squared to the 1/2, that's low, times, okay, what's the derivative of high? Two times negative 2x, so negative 4x, okay? And if you want to, like, remember, we could just also, maybe it's more convenient even, just to write this as 4 minus 2x squared if you'd rather. That's fine. So the derivative is negative 4x minus high, and let's just call it 4 minus 2x squared d low. So the derivative of that, what's that? What's the derivative of the bottom, everybody? 1/2 times 4 minus 2x squared, oh, x squared. To what power? Negative 1/2 times. Okay, and we could cancel 2's. And then, now what? All over low squared. Yep, sorry. All over. And what is low squared? Good. Okay, what could we factor out of the top? To the negative 1/2. Good. We have like. So again, we have some like bases here and some powers. Anything else we can take out? I don't think so. Where's a negative 4 in the second term? Where are you looking? So here's this is the minus sign that separates the two terms, right? I can't take it. Where do you get a 4 out of the second one? I guess we could take it. We could take a 2 out, I guess, if we wanted to, right? If we wanted to write this as, let's go back and write this. Oops. If we went back and instead replaced that with 2 times 2 minus x squared, I could take out a negative 2, I guess, right? That makes sense? Or even just a, does that make sense? Okay. So if I take out a negative 2, x, I can take an x out also. What's left behind? What's left behind from our first? So yeah, I'm going to get a 4 minus x squared. Okay, and that's coming from here. What else? Times 2, good. Times 2, okay. Oh.
Yeah, I know. I held up 3 and then.
There we go. So now what was left behind? So we got rid of, now this is gone. That's gone, which makes that a plus. That's gone. So all we had left was just 2 minus x squared. Because Oh, you're right. It's not a plus, it's a minus. You're right. You're right. Yep. My bad. You're right. Because we already have a negative there. You're right. Yep. So then we just have, all that we had left was just that guy, right? That factor. Everything else got undistributed. Am I right on that? Doesn't it seem like that's right? We took out the 2. We took out the negative. Took out the x. Yep. Okay. And then on the bottom we had our 4 minus x squared. Okay.
Yeah, I remember that. That was in art advisor, wasn't it? Yeah, that was somewhere. Oh, yeah. Me too.
Uh-oh. Somebody escaped. Okay, so there it was. There was our second derivative.
He's gonna finish it.
Okay, so now what?
Find the 0.
Where's that go? Okay.
That's what I was.
So in the denominator we've got what would that be?
Cubed.
To what power?
Just to the what? Just that?
I already have, what is, I have 4 minus x squared to what power right now? 1. And that negative 1/2.
To the square root of, so to the 1/2.
3 halves, right?
Are we dumb?
Well, because look, this is going to the bottom, right? So it's like I'm going to be multiplying that times 4 minus x squared to the 1/2, right? Okay. And then we've got our minus 2x out front. And then we just have to simplify all that, right? So we're just going to distribute the 2, distribute the negative, and we're going to get, what, 8 minus 2x squared minus 2 plus x squared. So 6 minus x squared. These are critical numbers. How about second derivative critical numbers? Where would they occur? Square root plus or minus square root of 6, right? Everybody get that? When x squared equals 6 or 0, okay? And square root of 6, do we need to consider those? Outside the domain, so we don't even care about those, right? The only ones we care about, only one we care about is at 0. And so how would we tackle this table? Yeah, but okay, so where would we evaluate the second derivative? At what values? Square root of 2 and negative square root of 2. And then you're killing 2 birds with 1 stone. You're doing second derivative test and you're testing for a point of inflection, right? So if we evaluate our second derivative at positive square root of 2, what are we going to get? So that's going to give us, negative times positive divided by positive, right? Okay? Which is negative. So we get negative there. What would it have been if we had evaluated negative square root of 2? Yeah, positive. Good, because that would have been positive, wouldn't it? we would have had positive times positive over positive. So what do we know then? Lots of stuff. What is this? Happy, good. So that's a minimum. How about this one? That's a maximum. What is this? There you go. And do we have a graph of this? Let's look at a graph of this. What's that? I pushed for it to not be second period. I always push for it to be in the morning.
Yeah, so they didn't like us and they were like, you're all gonna fail.
Yeah, it's a bad period for calculus.
Yeah, let's just talk. Why can't we just stay? Yeah, let's talk.
I think they should have switched Spanish.
Yeah.
But Spanish has always been fourth. No, but Spanish has always been fourth.
Yeah, but
I think we all
missing that?
Spanish fourth. They could have put
Because physics has to be first, AP, lit has to be one, it's taught to all at once. So,
I would rather miss that than count.
I'd rather miss any of those.
also,
classes.
you can have
One
those in the
has to.
afternoon because it he does like, it's not like, it's like, oh,
Okay, there it is. Here's what it looks like.
The problem with that though is like.
Okay, does that make sense? That fits, doesn't it? Okay.
That's when we won't.
Okay, quick reminder. If you're dealing with limits of rational functions at the infinities, remember what our rule was. If the numerator is a smaller degree polynomial than the denominator, then the limit at infinity is going to be 0, right? And you get a horizontal asymptote at y equals 0. If the degree of the numerator is equal to the degree of the denominator, then y equals the ratio of the leading coefficients. That's your horizontal asymptote, right? And then if the numerator is greater than the denominator, there is no horizontal asymptote. If it's 1 degree higher than the denominator, though, what kind of asymptote do you get? Let's say the numerator is a 4th degree polynomial and the denominator is a 3rd degree polynomial. What kind of? Well, you don't get a horizontal asymptote, but what kind do you get? Remember, you get an oblique slant asymptote, oblique asymptote, right? Okay. All right, so let's look at some that involve rational functions then. Okay, this is a big class of function you deal with a lot. So first of all, can you tell me about symmetry here? It is even. How come? You're right. You get the same thing, right. You get the same thing out that you start with if you evaluate this at negative x. You also know that the top is an even polynomial and the bottom is an even polynomial, and even over even is even, right? Either way you slice it, it's even. Okay, so symmetry we know. What's the domain? All reals. How come? You're right. Yeah, bottom is nowhere 0, right? So we're fine. All right, so what's next?
Even symmetry means it reflects over the x-axis?
Even symmetry means it reflects over the y-axis.
Oh, yeah, that's
Right.
right.
And the way, just always think about the easiest examples. X squared would be the easiest example of an even function, so it's a parabola, right? Vertex on the origin. X cubed would be the easiest example of an odd function with rotational symmetry about the origin. Okay, so what's next? Say it again. Oh, we don't care about that. We can do them if we want to. I don't care about those. Derivatives, yeah, we need derivatives. So differentiate away, what do we get? Low D high. So low, and what's D high? 2x minus, okay, times 2x over, okay, so if we, what can we do here? Well, let's go ahead and just distribute on the top. I mean, do you see on the top, rather than, we could just distribute and combine like terms and factor, but what could we factor out of each term? We could take it, not an x squared, right? Because I can't factor an x squared out of this one, but I could take a 2x out of both. Because how am I going to factor an x squared out of that first one, right? There's no factor x squared. See what I'm saying? The only common factor is 2x. If I take out a 2x, what's left behind? X squared plus 3 minus x squared. So what is that? X squared plus 3 minus x squared? 3. Yeah, right? So we just get 6x over x squared plus 3 squared.
That's not supposed to be negative. There's a mark on in the denominator of.
Oh, right here.
Yeah, but it's.
Oh, it's not supposed to be, yeah. I don't know why that's there. Like my hand just hit the board or something. So does that make sense? So what are our first derivative critical numbers? 0. And that's where the first derivative is 0, right? Okay. So we can add that. So what's that tell us about what's happening at 0 then? Horizontal asymptote. Okay. And second derivative. There's our first derivative. So what's our second derivative? What's the question? You don't have to. You could. You want to make it a product? Okay. Okay. So now what? Okay, so negative 12x, we'll pull the negative 2 out front, times x squared plus 3 to the negative 3 times 2x, okay? Plus
6 times.
yeah, good. X squared plus 3 to the minus 2 times 6. Okay, so if we clean that up a little bit, we get negative 24x squared times x squared plus 3 to the negative 3 plus 6 times the quantity x squared plus 3 to the negative 2. Okay, do you see any like bases? X squared plus 3. So what power of that base can I undistribute? Negative 3, the least of the two, right? And then I could also take out a 6. Okay? Okay, what's left behind if I factor all that stuff out? What's left behind from the first? That's it, right? Plus x squared plus 3, good. Okay, and if we just combine everything then and write this as a fraction, that gives me 3 minus 3x squared, right, times 6.
Yes.
And what else could I factor out to make that really clean? 3, yeah. Oh, and that's positive 3, isn't it? Okay, so what are my critical numbers of the second derivative?
Would be x squared minus 3 for the third.
Did I mess that up?
Plus or minus.
Oh, I think I wrote that wrong. That was supposed to be a plus.
Oh,
Yeah. So what are my critical numbers then? Plus or minus 1, yeah. And let's just make a note of that. So y prime equals 0 at x squared equals 1, so x equals plus or minus 1, right? Okay. Okay, so how do we proceed here? Test which value first? 0, yep. So if we test 0 in our second derivative, there's our second derivative. What do we get at 0? What's the sign? Positive, right? Positive times positive over positive. So that is, there we go. And then what else would we want to do if we want to find inflection points? Good, left and right of the second derivative critical numbers. So what are throw out some values then. What do you want to try? Okay, negative 2 and 2. Oops, too far. Okay, so at negative 2 and 2, we're going to get the same thing. What would the signs be?
Well, you're supposed to be negative.
We're going to get negative for both, aren't we? Right? Positive times negative over positive. Okay, so what's that make both of those? Inflection points. And we did some extra work, didn't we? We didn't really need to do all that, right? Because this thing has symmetry about the y-axis, we really could have just done this. We really could have just graphed, done that half of the table and then reflected it, right? I tell you what, it's dangerous to reflect the table, though. I think we talked about this. Which rows... We talked briefly about this. This part you got to be careful with. Which rows in the table, if I have even symmetry, would be the same? Remember? Remember what we said about that? It'd be y and y double prime, right? Y prime does not, like, to have symmetry in the function, the derivative is not symmetrical. Think about a parabola. The slope to the left of 0 is negative, to the right of 0 is positive. See what I'm saying? But the concavities would have to be symmetrical if the function is symmetrical, but not the slopes, right? So what's really easier to do there is just to graph half the function. Don't even make that half of the table, and then just reflect the graph, okay, if you want to use that strategy. Does that make sense? Okay. All right. Good stuff. Okay, what about this one? Oh, we forgot something important. We forgot the limits at infinity. We need the asymptotes. So what is the limit here? What's the limit as x approaches infinity? 1. How about as x approaches negative infinity? 1. Rational functions share a single horizontal asymptote, right? If it's a polynomial divided by a polynomial. So then we also have the horizontal asymptote at y equals 1. So if we wanted to graph this thing just to verify, okay. Everybody agree that's consistent with our table? Look good? -1, +1, those are the points of inflection where we change from concave down to concave up to concave down. Okay? Okay, what about this guy? Symmetry. What's the symmetry going to be? I think it does have symmetry. What kind? Odd, how come? Okay, so there's two ways to think about it. If I evaluate this at negative x, the only thing that's going to change is the sign of the numerator, right? So we're just changing the sign of the whole function. Okay. The other way of thinking about it is that that top polynomial is odd or even. Odd, right? Bottom one is even. Odd divided by even is odd, right? Odd acts like negative, even acts like positive with sign conventions. Okay? Either way, we'll do this one. So odd. What's our domain? This is an interesting one to look at. What's the domain going to be here? What values are excluded? One or -1, right? We have to exclude values where x squared equals 1, so plus or minus 1. Give me thumbs on that. Does that make sense? Okay, from the denominator. Whoops. Okay, what's going on at those places? Plus or minus 1. Only two possibilities if you have a 0 in the denominator. Either it's a whole or an asymptote, right? Which one is it? How do you know if it's a vertical asymptote? Vertical asymptotes occur where zeros of the denominator only, right? Vertical asymptotes occur at unique zeros of the denominator. So wouldn't you agree that only the bottom, the zeros of the bottom are plus or minus 1? The top is not 0 at positive 1, nor is it 0 at negative 1, right? So that is what's going on at those places? Vertical asymptotes, right? Because I would get 3 over 0 or negative 3 over 0, right? Okay. Okay, that's a lot of stuff we have right away. What about horizontal asymptotes? What's my limit going to be as x approaches infinity? And you could do this any number of ways, right? The way we did this the most efficiently at the beginning of the year, because these are polynomials, they're dominated by their leading terms, right? So the limit of a polynomial is the same as the limit of its leading term as x approaches infinity. So we could just look at the ratio of the leading terms. 3x over x squared is 3 over x. So the bottom's going to explode, and the fraction goes to 0. You could use L'Hopital's rule. Right, this is infinity over infinity. The derivative of the top is 3, derivative of the bottom is 2x. So again, you're just going to get 3 over infinity, which is 0, right? Either way you do it, you're going to get a limit at 0. Okay, so we got a bunch of stuff out of the way. We know what the horizontal asymptotes are, the vertical asymptotes. We know the symmetry this thing has, and we know we know lots of stuff. So now we just need to find derivatives so we can see if there's any extrema or inflection points, and we're done. Okay, so first derivative. What do we get? Okay, good. X squared, low is x squared minus 1 times d high is 3 minus high times, what's d low? 2x over x squared minus 1 squared, okay? So what's that give us? We really can't factor, we can factor a 3 out, I guess. What if we just distribute? So we get 3x squared minus 3 minus 6x squared on the top, so negative 3 minus 3x squared. And then I could factor out a negative 3. And what's left? X squared plus 1? Okay? Critical numbers. What do you think? Is that right?
No, I was just saying, like, why not just factor like instead of negative 3, just 3 with the 9, it's negative x squared.
Yeah, I mean, same thing. Just a little bit easier to think of as x squared. Yeah. Okay, so where are the zeros of the first derivative, or are there any? None, right? Because the numerator is never 0. Right? This term x squared plus 1 is always positive, isn't it? Any zeros of the denominator? 1 and negative 1, but are those critical numbers? They're not. How come? Those are asymptotes. They're not in the domain, right? Those are excluded from the domain, so they can't be critical numbers. Critical numbers have to be in the domain. Okay, so we get no first derivative critical numbers. Second derivative. And let's maybe go back up to here for our second derivative, where we haven't factored the top at all. So second derivative. Low d high, right? So there's low. What's d high? Negative 6x minus high d low. Yikes, what's d low? Times 2, okay. Times 2x. So 4x times x squared minus 1. Agreed? Okay. Okay, so then what if we, and all over x squared minus 1 to the 4th. Okay, so let's see if we factor out, why don't we just factor out, and this is going to get complicated. What if we just factor out, let's clean it up a little bit. That's too messy. Over here, what if I take that,
We got a -3.
take out, yeah,
Or 3. So you can take out, so you can factor -3 out of
yeah, we could take out a -3, which makes that positive, right? And then we just have 1 plus, okay, we'll do that. Take out a -3 times a -1 is 3 times 4x. Okay, check that, everybody on top. Does that make sense? So this stuff, what got combined here? So that I took out a -3 and a 4x, right? Everybody see that? And that gave me 12x. Good? And then that became 1 plus x squared, or x squared plus 1, and then x squared minus 1, over x squared minus 1 to the 4th. What could I factor out and cancel? Okay, everybody see that? Look, I've got an x squared minus 1. I could cancel one of those from the top and just make that a cubed, right? And then I could factor out 6x, okay? So then that's going to give us, what's that going to leave us with then? We're going to get 6x. That's going to leave us with negative the quantity x squared plus 1 plus 2 from that side. Oh, 2 times x squared plus 1. Oh, that's supposed to be minus 1. Whoops. Right, because we had one of those left over. And then here we've got a 2 and then this guy. So if I distribute and collect like terms, see if we can do that all at once. How many x cubes are we going to get?
X squared minus.
So it looks like, I'm going to get negative x squared plus 2x squared. So I'm going to get 6x cubed. Everybody agree?
Yeah.
Okay. How many, what else do we have? How many x's? We're going to get plus 6x plus 12x, so 18x over that. And I guess, why did I really could have just left the 6x out front. Why did I distribute it? That was dumb. We'll just see what I'm saying. It's already factored. There's no reason to do. We already had the 6x out front. Just combine everything in the brackets. 2x squared minus x squared is x squared. Plus 1 plus 2 is plus 3, right? So are there any second derivative critical numbers?
0 and
0, right? Because there's x squared plus 3 is never 0. But 6x is 0 when x is 0, right? Okay, so y double prime, there is one second derivative critical number. Second derivative equals 0 at x equals 0. So we can make our table. And we had some, we excluded 1 and -1, right? So -1 was a vertical asymptote. 1 was a vertical asymptote. And we said, oh, what's the sign of the second derivative at 0? Oh, actually, it's 0. Right, so what do we need to do between the vertical asymptotes? There are no extrema anywhere, right? There were no first derivative critical numbers. But what could be happening there? Could be an inflection point, right? That's the only thing it could be is an inflection point, right? Okay, so is it going to be an inflection point? Do you think? If the symmetry is odd? See what I'm saying? You guys told me it was odd symmetry. So if it's got odd symmetry, if it's got reflective symmetry about the origin, do you see that has to be an inflection point? It has to be, doesn't it? Yeah. We'll finish this one up tomorrow.